My name is Guilherme Brando. I'm a PhD student at the Universidade Federal do Espírito Santo in Brazil. Today I'm going to talk about relativistic effects of modified gravity in the growth of structure. This work is based on a paper that is yet to be to appear on arXiv. I think it's going to be available by the time of our meeting, but by the time of this recording, it's still not available. This work is also done in collaboration with Kazuya Koyama, David Wands, Miguel Stumalacarregui, Emilio Bellini, and Iggy Savitsky. The outline of this talk, I'm going to talk about the introduction first, discuss the motivation of our work, why we need to introduce relativistic effects of modified gravity in the growth of structure. Then I'm going to move on to the framework in which we use to introduce these relativistic effects, which is the N-body gauge. I'm briefly going to talk about the modified gravity theories in which we used our formalism with. And then I'm going to present the main results and investigation and analysis of our investigations within this framework. To finish, I'm going to conclude with the conclusions of our work, and then I'll talk a little bit about our perspectives for future works. So, as everybody knows, here in this meeting, and I think most of the people already know, the standard model of cosmology, general relativity is assumed in all scales. So the gravitational interactions throughout the universe, so from small scales to the largest scales, is always described by general relativity, which is based on the Einstein tensor plus cosmological constant and the energy momentum tensor of matter species. So also within the standard model of cosmology, we know that the cosmological constant is the cause of late time acceleration, and this is the phase in which we are now experiencing it at present time. So this late time acceleration that is now confirmed by several different probes is described and as an unknown fluid called dark energy. And within general relativity, the simplest explanation for this is this cosmological constant lambda here. However, as we know, there are other ways in which we can explain this late time acceleration. And one of these other avenues is to use modified gravity. So in modified gravity, there is sometimes, in the majority of the cases, there will be an extra degree of freedom. These extra degree of freedom will be present and dominating at late times, and then this will be these extra degree of freedom will be the natural explanation for the late time acceleration of the universe. In most of these theories, there is no need for the cosmological constant to be present, and that's why they act as alternatives to them. But there are some specific models in which we still need modified gravity plus a cosmological constant to realize these accelerating expansion at late times. However, as always, we need to accurately probe and test these modified gravity theories. So this is basically the point we are at now in the modified gravity community. We need to come up with ways of probing, of testing gravity throughout in all scales in the universe. So basically, we already have multiple constraints on gravity coming from different regimes, different probes, and so on. We know that the most stringent test, the most constraining tests we have so far of gravity are astrophysical and solar system ones. So in this picture that I present here, it's a little bit outdated. I know it's from 2013, but it gives a nice idea that what is the measurement that we have, so measurements of the path of gravity that we had, and the general relativistic predictions. So basically, this is this horizontal black line along the one value. These three black dots in the beginning, they lie pretty much close or on top of this straight line, and they represent solar system and astrophysical tests. I write here solar system, but I forgot to write astrophysical tests. But these tests are always conducted. They were conducted in regimes in which the scale was pretty small, and also the density of the environment it was pretty high. So, however, of course, when we move to cosmological scales, so scales that are bigger and also they're less dense, these environments, we still don't have as competitive tests as we have when we compare it to local tests. So, for instance, again, this is an outdated plot, but this point over here is now, for instance, can be a little bit down nowadays, but still it's not as comparable as we have from these measurements of astrophysical and solar system tests that are below 1% precision. We still don't have the same accuracy as we have in these local tests as we have in cosmology. And the question is, how can we improve these tests? So we know that in the near future we will have Euclid as and then a while later LSST. These galaxy surveys, they will increase the amount of data that we have of cosmology. We will now probe with sub% accuracy scales below scales around and bigger than the scale of equality between matter and radiation, and we will now probe also the largest scales we have in the universe. So we will be able to go closer and closer to the cosmological horizon. And the bulk of information of all of these data that will be available will lie in the nonlinear scales. And the best way for us to model these nonlinear scales and the most accurate and so on are n-body codes in which we have big simulations. So we have to perform Newtonian n-body simulations, and we can accurately model gravity in GR and also modify gravity in these regimes. But I'm not going to talk about general relativistic simulations. I'm going to talk about modified gravity, Newtonian simulations. And the problem with these modified gravity Newtonian simulations is that they only account for dark energy effects that are caused by or sourced by matter perturbations. So this is a valid, and these effects are accurately modeled and described in small scales, where we know that Newtonian gravity is a good approximation. And they are commonly referred to fifth force. So we have a fifth force. So since we have two mediators of gravity, so we have the metric tensor, but also the scalar field or other field. This other field will introduce a fifth force. And in this case, what happens is that the Poisson equation, it is now the gravitational coupling between matter and the phi potential is not now constant. It will be a function that depends on tau and scale. And it is encapsulated by this G effective function over here. So this is the concept. This is how we introduce modified gravity effects into these Newtonian simulations. But as I already mentioned in the previous slides, at short distances, so these small scales, we must have also some way to restore general relativity, as we know that general relativity is the correct description in really small scales and really dense environments. And to shield these extra force that appears when we are dealing with modified gravity theories, we often invoke and have to introduce screening mechanisms into these simulations also. So this screening mechanism will ultimately shield and block the modified gravity prescription at these scales, and then we can restore general relativity. At the same time, we have now to accurately model the other side of the spectrum. So at large distances, where we know that is where the accelerated expansion can be probed. So at scales around the Hubble scale, so near the horizon, we need to now we have to introduce modified gravity effects that are not sourced only by matter perturbations, but also sourced by other fields. So we have other source terms that are now contributing to modify gravity in these really large scales. To better understand the scenario, I think this is a good figure, because what it's basically saying is that in a very small, in the center, we have this, in the center circle, we have general relativity, which will be the smallest scales in the universe. Then we have this green shaded region around here, which I dubbed LSS, large scale structure, where in this case we will have two mediators. We will have we will see that modified gravity will be described by this phi scalar field, which will be the modified gravity at hand. And this phi scalar field will introduce this fit force. And we will also have general relativity. However, as we go to larger scales, we will have to accurately model not only the effects introduced by modified gravity from this fit force, but also other terms. So this is the scenario that we are now at hand, and this is the scenario we have to deal with modified gravity to improve our cosmological tests. So the way to the path that we can take to introduce these relativistic effects in modified gravity simulations I'm only going to list two. The first one is the weak field approximation, in which I'm not going to discuss any further, but is based on a weak field approximation. It is an inherently relativistic simulation, because it's performed using the Poisson gauge and so on and so forth. We have different speakers talking about this path, which is normally used when you use the relativistic n-particle G-evolution. And in the case of modified gravity, we have the clustering dark energy counterpart that is called K-evolution, which was introduced and developed by Farbod Hassani and collaborators in these two works over here. And I think that Farbod is going to give a talk also in this meeting. So for more details, I think it's better to go directly to the source than listen to me talking about it. The other way that we can introduce relativistic effects into modified gravity simulations is to use a specific gauge. So this is this is already a well-known fact that we can interpret the output of Newtonian simulations within a specific gauge choice. This was introduced and developed by Cesare and Santariaga. But after that, a few years after that, Christian Fiedler and collaborators, they introduced the notion of this n-body gauge, which is a specific gauge in which we can interpret the output of Newtonian simulations with relativistic corrections already accounted for. And later on, another gauge appeared in the literature, the n-Poisson gauge, which is a mix between the n-body gauge and the Poisson gauge. But I'm not going to focus on the n-Poisson gauge and other gauges. I'm only going to develop and work on top of the n-body gauge. So now I'm going to briefly describe and give a brief description, very reduced, on what is the n-body gauge. So basically, what the n-body gauge is the following. So when we compare the cold dark matter dynamics in its Newtonian formalism, so on the left-hand side we have the Newtonian equations of motion for cold dark matter, and on the right-hand side we have the general relativistic linear order description of cold dark matter. And we can see that we have three terms on each of these equations that will introduce relativistic corrections. So we'll introduce relativistic deformations from the Newtonian description. So the first one is a temporal one, where we can choose a specific temporal threading and then just, for instance, remove the dependency of this term over here. The second one is in the continuity equation. So this is a very interesting aspect that, so in the presence of this time derivative of the spatial trace perturbations, this HL potential over here, it introduces deformations in the volume elements. So in the end, what we have is that the naive density of counting particles in a Newtonian simulation will not be equivalent to its relativistic density. So, and this is precisely due to the presence of these spatial trace perturbations. And the last term is related to is present at the Euler equation. And we can see that it's a little bit trickier, but it mainly consists of terms that appear in traceless parts, both in the metric, so the HT potential, that is the traceless spatial perturbation, and also in the anisotropic stress of particles. So the n-body gauge is precisely this choice that I mentioned before. It's precisely if a choice that your temporal threading is going to be the comoving. It's going to be it will be a comoving gauge in which the shift perturbations will be the same as the for velocity, and the spatial slicing of the spacetime will be set to we won't have any deformation to the volume element. So HL, the spatial trace part of the perturbations of the metric, will be 0 as well. So in this way, we can already see that both the Poisson and the continuity equation, they are already in the same form as their Newtonian counterpart. And in the case of the Euler equation, we have this extra gamma NB potential, which encompasses all the traceless contributions, both from metric and from matter species. And the fun fact is that in the n-body gauge, we can write this HT contribution solely in terms of fluid quantities of the matter species. So the anisotropic stress, the pressure perturbation, and the total divergence. And by doing so, what we see is that since cold dark matter has no pressure and no anisotropic stress, at linear order, everything on the right-hand side of this equation will be 0. And then gamma and body, so gamma and B, the relativistic potential, will be 0 for the case of cold dark matter. And then we will have this one-to-one correspondence between linear relativistic dynamics of cold dark matter and Newtonian dynamics. So in summary, the n-body gauge is a gauge in which we don't have any deformation in the density of particles. The relativistic matches the counting of particles in Newtonian simulations. The equations of motions for non-relativistic matter, they match. They are the same at linear order, both in relativistic and both in Newtonian. And we can safely introduce the effects of photons, neutrinos, and dark energy at large scales if we merely add on the combination of these. This is the equation. This is the combination of the continuity and the Euler equation. The effects at large scales, they will be merely encoded in this delta rho gr source term over here, which is the sum of the density perturbations of the relativistic species plus a term that is related to the traceless contributions of the metric. So in bottom line, on the left-hand side, we will have the same dynamics as Newtonian gravity at small scales, while on the right-hand side, we will have the dynamics that are relevant only at large scales. And when we solve these in a simulation, if we introduce these delta rho gr term into a simulation, the output of the same simulation will already be in the n-body gauge, because the n-body gauge doesn't affect the dynamics at small scales if everything that we are considering is always at linear valid at linear theory. For instance, photons and neutrinos contributions are always subdominant at smaller scales, and the dark energy contributions, I'm going to talk about them in a bit. So our implementation of how we can compute this delta rho gr is bottom line the following. So it's only relevant at large scales. So linear theory is valid. So we can then use an Einstein-Boltzmann solver. As we are mentioning and working with modified gravity theories, we chose to work with high class, which is a modified gravity theory Einstein-Boltzmann solver. We have to compute delta rho gr inside this code, which is going to be very accurate. And the first three terms are basic and straightforward on how to output them. We just have to gauge transform the quantities from high class that are already in the synchronous gauge, and we just gauge transform them into the n-body gauge by the following equation. So it's pretty easy. The last term is a little bit trickier because we need to compute that gamma potential that I mentioned before, which involves first and second time derivatives of traceless contributions of the metric and the anisotropic stress. However, since we can compute HT in terms of fluid quantities, we can also compute the same quantities inside high class. So everything can be outputted in a very straightforward and quick way. Einstein-Boltzmann solvers are known to be fast and low cost, and that was our main idea, to output this delta rho gr by computing HT and HT dot and HT dot dot inside them. So just an FYI, so to compute all of these quantities, we just use the Boltzmann equations for photons and neutrinos. So both of these species have governing Boltzmann dynamics. So we have an equation for sigma dot and delta p dot and theta dot, not delta p dot, but delta rho dot. And we can straightforwardly compute them. However, what about the dark energy contributions? These are a little bit trickier because we don't have a specific Boltzmann equation for them. We don't have a correspondence between density perturbations and anisotropic stress perturbations in general modified gravity theories. And for this, we actually did a little bit, we chose a different path. So we chose to work with Horndeski theory, the most general scalar tensor theory with second order equations in both fields, so scalar field and metric tensor. The action is known to be big, it's very messy, but we can use it simpler formalism, which was introduced by Bellini and Savitsky. And it consists basically in choosing a background in which we just choose the expansion history of our universe. So we can choose a parametric version of dark energy. So for instance, W0 WA, or we can choose lambda CDM. And whichever we choose, it will fix all of the freedom in the background. And as for the linear perturbation theory, we have only 4 free functions of time that fully captures all of the physics in these Horndeski series. The first one is the kineticity, alpha k. It mainly encodes notions and terms involving the kinetic energy of the scalar field fluctuations. Alpha b, the braiding, is just a mixture between scalar field contributions and metric contributions. Alpha m is the running of the Planck mass. So in these theories, the Planck mass can be time dependent, and in this way, alpha m is just the time derivative of these Planck mass. And the last one is alpha t, which is the tensor excess, and this basically saying to us that in Horndeski theories, gravitational wave speed may be different than the light speed. However, since the binary neutron star merger, we know that the gravitational wave speed, they propagate at the same speed as light. So alpha t is constrained to practically 0 nowadays. So, but the question at hand is precisely this. We need to compute the anisotropic stress and the pressure perturbations of dark energy. And for this, since in Horndeski theories, the Bianchi identities and the conservation of energy momentum tensor are satisfied, we can just use this effective fluid description and move modified gravity theories effects from the left-hand side of Einstein equation to the right-hand side. And then we treat these modifications of gravity as an effective energy momentum tensor, but it's just some redefinitions of the quantity. So it's not precisely a energy momentum tensor. It's just an effective view of these equations of motion. So what we then have is that at linear order, we can isolate GR contributions, which are on the left-hand side. And on the right-hand side, we will have the usual fluid quantities and perturbations for CDM, baryons, neutrinos, and photons. And we will also have for dark energy. I will not show the precise form of these quantities for dark energy because they are very lengthy. But bottom line, they all depend on the same quantities that we already have on when we solve high class. When we use high class, basically what we have in the end is the output is basically the synchronous gauge metric potentials and the scalar field fluctuations. So we can just rearrange them in a specific way to in the end we have the same to have the delta PD and also sigma D. So it's just a mere recasting of the equations of motion that high class is already solving. Specifically, we want these two quantities over here so we can feed it to the computation of gamma and body. And once we have gamma and body, we have HT dot and HT dot dot, we can evaluate all of the quantities of delta rho gr. The first three that were merely gauge transformations, and the last one that is just some redefinitions that we are allowed to do inside the code. Basically, this is our formalism. This is the idea. We can compute delta rho gr and feed the source term into Newtonian and body codes to make the output already relativistic and consistent with the n-body gauge. So I'll now show the results. So first, I'm going to show the effects that we have at extremely large scales in the matter power spectrum. So we chose to fix the expansion history to be the same as lambda CDM. The alpha functions, so the braiding, the running, and the tensor excess, they are just proportional to the fractional energy density of dark energy. This is a very basic and common parameterization. And the kineticity, we chose to kept constant throughout the expansion history. So it's always going to be constant to a fixed value. We show here the relative difference in percent of the matter power spectra computed solving the linear Newtonian matter power spectrum, this equation over here, and PGR, which is we solve this equation, which is basically the matter power spectrum, matter power spectrum in the n-body gauge. So we can see that we have different models of gravity over here. I'm not going to dwell in them, to go deep in them. This is a modified gravity which we only have running, so there's only alpha m. This one is a very famous one, which is a parameterization that follows Jordan-Brans-Dicke theory, but it's not a covariant theory. It's just a parameterization, but it can be parametrized this way. And this one is a case where we only have braiding. We didn't I'm not going to present. We analyzed, but I'm not going to present the results for the only alpha t case because, as I said before, it's not a very relevant case since alpha t is basically zero by gravitational waves cosmology. So we also varied the kineticity for three different values. So we varied from 100 to 0.01. And we can see that at extremely large scales, we have this big amplitude, big enhancement in the amplitude of the signal at these scales. So this is basically caused by the source term in the scalar field fluctuations equation of motion. So the only source term in this equation that is relevant at large scales is precisely a term that is proportional to the sound speed. And since the sound speed is inversely proportional to the kineticity, the smaller the kineticity, the bigger the sound speed. So in this way, this big enhancement is caused by this big value of the sound speed that the scalar field travels. So, but the question also is also, what about the other scales? What is happening around here? And this is now what I'm going to discuss. So To better understand the behavior at the intermediate and the small scales, we chose to separate the effects of dark energy from both scales. So we'll be using the quasi-static approximation, which is valid deep inside the horizon, and is what Newtonian modified gravity simulations also use, because, as I said before, Newtonian simulations in modified gravity, they just introduce the effects coming from G effective, which is the fifth force, and we can compute G effective and also separate the large scales from small scales using the quasi-static approximation, which will basically have, say, that the density perturbations and the anisotropic stress perturbations in small scales will be proportional to the matter density perturbations. So in this way, we are going to write delta rho d and also sigma d in two terms, a QSA one, which is the Newtonian one, plus a relativistic one that is only relevant at scales that are not so small. So to show the consistency and the agreement of this formalism that we introduced on high class and to have our results, I'm going to show here three cases of kineticity. So the same modified gravity theory, but for different kineticities. And we see that the curves do, so the full perturbation compared to their QSA counterpart, they do overlap when we go to smaller scales. So at smaller scales, we are actually in a regime where Newtonian gravity is a correct description. So the bigger the kineticity, the smaller the sound speed. And with this, what happens is that this agreement is pushed to larger k, but it will always occur. So let's just take a step back and remember where we are. First, we have that modified gravity Newtonian simulations do not capture relativistic effects, only fifth force effects. And the n-body gauge allows us to introduce large-scale effects in the source term delta rho gr, but the effects coming from dark energy, they are mixed together. They are not separated. So there's not a direct correspondence from modified gravity Newtonian simulations and the n-body gauge in modified gravity. But when we use the QSA, we are allowed to separate these two effects by just writing the delta rho d and sigma d perturbations in this way. So we can just shift part of the contributions that were on the right to the left-hand side, and then we are with the same left-hand side that usual modified gravity Newtonian simulations and body code. So I'm going to show some plots also in which this new quantity is going to appear. So PNG effective, which is the matter power spectrum that we build from this solution, and PGR, the matter power spectrum that comes from the solution of this equation. So first, we see that also consistently and as we expected, the effects in small scales coming from G effective, they are mitigated precisely because before, as I showed, when we don't introduce G effective in Newtonian simulations, we just solve GR Newtonian simulations and compare to PGR, so the fully corrected Newtonian relativistic matter power spectrum, we have this shift, vertical shift at small scales that is mainly caused by G effective. And once we solve this equation, we show that this vertical shift now disappears because the small scales is precisely the same in both matter power spectrum. Also, I show here the smooth transition of our formalism to Newtonian gravity. So what we want is that the perturbations in the energy density do not exceed the perturbations coming from matter perturbations. So we don't want that these curves are bigger than 1%, or in this case, we chose to be bigger than 0.1% at scales in which linear theory is already known to be not valid anymore. So around 0.1 and 0.12. This is just the sound speed of these cases, just to get an understanding of what is going on with the scalar field throughout the expansion. And another interesting and very relevant result from our work is that we have bigger than 1% deviations around scales that will be probed in the near future by the next stage for LSS surveys. And these effects, which are purely relativistic effects, they don't come from G effective, they don't come from QSA. They are not actually being modeled yet by modified gravity Newtonian simulations. So we need to account for them in order to have a consistent and precise description of modified gravity Newtonian simulations. To finish, I'm just going to show briefly these plots over here. So the models that we chose, we fixed the kineticity, and it ended up that we have some gravity acoustic oscillations in scales from 10 to minus 3 to 10 to minus 2 in the matter power spectrum for kineticity values that are smaller. So low and small kineticity values and big sound speed. So we can see that in these two panels over here, the top panels show the ratio of the scalar field fluctuation that is fully relativistic with respect to its QSA counterpart. And once the mode crosses this dark energy sun horizon, it is allowed to oscillate. Because once you cross the horizon, there are pressure gradients coming from the scalar field that end up counterbalancing gravitational interaction. So they cross the dark energy sun horizon, they oscillate a little bit, but then they are eventually damped. And the damping is precisely not only from the damping that comes from the scalar field fluctuation equation, but mostly from the QSA. So what is happening is that once you go to smaller and smaller case, matter density perturbations sourcing the dark energy ones, they end up dominating the full perturbations, and the same oscillations that we see here, they eventually die off. So to conclude, we have relativistic effects of dark energy that are not accounted for in modified gravity simulations, but they can be readily implemented with our formalism using this delta rho gr. The kineticity enhances the signal at large scale. We observe the emergence of these gravity acoustic oscillations at large scales, and they can be, in theory, amplified to possibly detectable levels in models in which we have this rapid dark energy sound horizon evolution when compared to the usual cosmological horizon. For the future, we are now in a position where we can move to the next part of our project, which is to introduce this formalism in a Newtonian modified gravity simulation and actually test and validate our results. So when we have also another fully relativistic MG simulation, which is the one provided by K-evolution, and it's going to be interesting for us if we can cross-check our results with their results, if not only we introduce relativistic effects at large scales, but also this clustering dark energy model in a Newtonian modified gravity simulation. So thank you very much for watching this presentation. I look forward to meeting virtually everybody in our next meeting. And I want to thank, I forgot to thank the organizers in the beginning for giving me the chance to present my work and get some feedback of our results. Thank you very much.